That's good. All right, so, oh, beautiful, huh? Computer's like struggling. Okay, now it's good. So, I'm recording. I just want to make up an example. Maybe I should like face the microphone. The microphone's that way. I just wanted to make an example where, just a silly one. Let's say you got a box, very exciting box, and it's being pulled by a rope, and the person's dragging it. Is everybody good?
Yeah.
And the mass is m. I'm not going to use any numbers. I think it's good for you. You can solve problems with numbers, all right? I'd always encourage you, though, to solve problems in general. That's how I'm going to do it, all right? And I'm just going to say this mass is moving with a constant velocity to the right. Is everybody good there?
Yes.
In fact, I'm going to turn that vector into a motion map, okay? So there's my motion map. Are you guys good? It took me about 10 seconds to do that. Shouldn't be a big deal, right? And A is 0. And I'll make this way positive in my picture, just to make it simple. Are you guys good? So my velocities are positive, my acceleration is 0. Hee. Okay. So how would we go about solving this? Well, first and second step are identical no matter what approach you use. So maybe I'll circle this and move this over. This is identical. Then you would identify your system, which I'm guessing is the box. Are you guys good? All right. And then this dot now represents the box. Everybody happy so far? And we've done this. Name a force and give me the direction, please. Okay, wait. This is the vector you just figured. Now you have a way to calculate the length of this vector if you know the mass, right? So I'll call that weight, and I'll write Earth. Earth slash normal force. Which way, please identify? Good. Normal force up. Very nice. Okay, and I'll call that normal. Oh wait, I've learned I want this on the other side. Sorry about that. Normal, and this is surface acting on box. Everybody happy? And notice I'm identifying the cause of every force, always. Later, we can take off those labels and just have normal weight, and that'll, but in your mind, you need to say it, okay? You need to say what's causing every force. What else, please?
Friction.
Which way? Okay, we got friction. That would be kinetic friction in this case because you're sliding, and that's due to surface acting on box. Everybody happy? Then what else?
Force applied.
Okay, we got a tension force, yeah? Good. And here's what I'm going to do. I'm going to draw it right near here, and I'm going to take special care to make sure my line is parallel to the rope in my diagram. So you make sure your diagram is accurate, and then you make sure your force diagram accurately reflects your diagram. That's a way to check your work as you go. Are you guys good?
Yeah.
So I spent extra care to make sure that angle was correct. T rope slash box. And you may not realize this, but in a situation like this, something like that, I'm going to make it a generic angle theta. Are you guys happy? Okay. So this is pretty classic medium to easy level AP problem. Okay, this is a very easy one. I'm starting you easy here. Okay, so now I'm going to translate that to my force diagram by using reference lines. So I'm going to draw a reference line there. Okay? Reference lines are really valuable. And then I'm going to label my angle. Okay? There's my angle there. Are you all happy so far?
Yes.
Okay, now zoom out. You don't sound happy. I'm just playing. Anyway, so at this point, there's really two methods that I see quite frequently. And I prefer one of them. I'm not going to tell you which one, only because I think it's more elegant. And I like geometry more than algebra, personally. It's just more beautiful. But algebra is like, calculus is algebra. And I took calculus a couple times only because I loved it. Like the first time I took it, I aced it. The second time I took it, I aced it. Third time I took it, I aced it. And I took it again and again just because I loved it so much. I don't know if that makes any sense, but it just seemed very interesting. And even though I did well, I knew I didn't understand it after I got a good grade. Like it's totally possible to ace it and get it, and you don't know it at all. And that's how I felt. So I took it again and again. Anyway, I'm that one. All right, so I'm trying to pick which method. I'll divide the methods up here, okay? Maybe I'll divide it to the screen like that. So kind of organizing my work. In terms of grading your work, I don't have a choice, right? I have to grade your work. So I'm limited to setting up rubrics and the things I look for. Diagram, check. Motion map, check. Force diagram, check. Make sense? And the AP board's exactly the same way. Everything you do, whether you solve the problem or correctly, everything you set it up beautifully and organize it. Okay? So I got my diagram, my motion map, my force diagram, and I know that's correct. Cool? Ray looks like he's having fun. Anyway, so at this point, here are the two approaches I use. I'm going to call this one the vector sum diagram. And that solution will be more geometric style. And this is the axis only force diagram method. Okay? Well, that was beautiful. If I turned it into a line. Alright, so I'll explain the methods in a minute. To do the vector sum diagram, pretty basic. You just draw a. I'll try that again. To do the vector sum diagram, you just simply draw a. Yeah, head to tail vector sum diagram. And in this case, is N1 valid? Does the object have any acceleration? Yes.
No.
So, since you need to set up this beautiful logic, it's probably, and then you make that beautiful N1 statement, and then you back it up, right? You back up your statement by saying, yep, that's N1, and then you can proceed to add the vectors. So again, I'm going to make special care to put my tension in the proper direction. I'm going to make weight going down, and I'm going to make friction to the left. And I'm going to add the vectors in such order that it creates a beautiful, simple shape. Make sense? You can always redraw your vector sum diagrams. I'm cheating because I've done this problem before. No one's going to tell you which order to add them. You're going to have to figure that part out yourself. Make sense? And the solution becomes simpler if you add them in a specific way that makes a simple shape. Then I'm going to label my vectors. Now, what can I replace weight with? Everybody yelled it out.
Force.
Gravity, field, strength, times.
Earth. No.
What? No, I didn't say that.
We just did this. Replace weight with what? Mass times. All right. Are you guys good?
Yeah.
So that's what we got out of that lab. Now we know the length of that vector because we know the mass. We just multiply the mass by 10 newtons per kilogram, and we get the weight. Are you guys cool?
Yeah.
So I'm going to label all my vectors. Friction, this is normal, and this is tension. Are you guys cool?
Yeah.
Alright, now there's a couple ways to do this. I could just use this triangle here, and I could solve it. And I could find this length, I could find that length very easily, and then I can solve for stuff. You guys good? Now, I kind of been playing around with other ways of doing it, and you can also easily do this, right? These two red vectors are sort of nice to draw, because then you can see, and I don't want you to think tension, whoops, haha. Let me go back a step, because my tension is like in a bad spot there. It's in my way. Okay? So now I'll redraw this. Okay? Tension's actually this one here. Don't confuse it. Okay? Well, do you guys see that this angle is also theta? So this side here and that side there, we can easily figure out. Do you guys know how? Sine and, are you guys good? So sine theta is going to be, I'm going to define this as tension in the y direction, and this one as tension in the x direction. And I'm defining x and y as horizontal and vertical in this case. Are you guys good? So sine theta is going to be ty or tx? Ty over t. So that means that ty is t sine theta. Is everybody happy there? Alright, and I can do the same with cosine. Cosine is going to be tx over t, which if I simplify that and solve for tx, I get tx equals t cosine theta. Are you guys good? Alright, so now I can see from my vector sum diagram what's equal to friction. Bam. And what's equal to weight? Bam plus. Are you guys good? So I'm going to just write those out. And typically the verticals will tell you something and the horizontals will tell you something. So I'm going to argue that, okay, friction has to be equal to Tx, which is equal to T cosine theta. So if I'd given you tension and mass, you'd be able to solve for friction. Make sense? And then from the other part, I can write the equation mg equals what? Ty plus n. And notice that if I gave you tension and mass, you would be able to then find normal, which in this case is going to be mg minus ty. Are you guys cool? What I like about drawing a vector sum diagram is its elegance and simplicity. Now on the other hand, the traditional method, this is the way I was taught, it kind of annoyed me. I'm going to take any vector that is not in my defined x, y direction. See how this is positive y direction and this direction is positive x direction on my diagram? And you are allowed to tilt your coordinates to capture more vectors in some cases. But in this case, if I just make y up and x horizontal, the only vector I'm not capturing with my axes is that one. Are you guys good? Be a bad time to tune out. So again, the only one, you put your boards out, I think it's hard for them to see back there. So I'm going to redraw the only vector that's not along my xy axis, okay? Which is tension. And I'm going to break that vector into its component vectors, into its pieces, okay? In the x direction and in the y direction. So that's my tension. This is my y-axis. This is my x-axis. Are you guys good?
Yeah.
All right. If that's my tension, I'll call that tension P. Then guess what? Green vector to the right. Do you think that's tension in the x direction or y? And this one here is x or y. Okay. So by logic, can I say that vector Tx adds with vector Ty to get me the vector T? Do you see how the vectors Tx and y are head to tail? You guys good?
Yes.
So the logic goes something like this. Let's make an axes-only force diagram. That is a force diagram where all our forces are either in the x or y axis as we've defined them. Good? So if I replace tension with the two that add to it, the component pieces that add to tension, if I replace the tension with the components, then I'll only have forces along the x or y axis. Okay? That makes it so that you can treat the vectors as scalars with positive, negative as their direction. That's what it gains us. Okay? So here's my y-axis. Now I'm just going to redraw. Do you understand why this is called an axis-only force diagram now? All the forces are on our defined. There you go. So we're putting all our forces. We're breaking up any force that isn't in our xy axis so that it's along our xy axis. And however many forces are not along your defined xy is how many forces you have to break up into pieces or component vectors. The components must add to that vector so that you can replace the vector with the components. I know that was confusing. I think when I draw it, it'll make more sense. So when I draw it, I'm going to replace t with what two vectors? Let me do that one first. Okay, so I'm gonna draw Ty. There's my Ty. You guys happy? And then Tx is this way. Are you guys good? That was kind of nasty here. There, that's good. So there's my Tx. Are you guys happy? Okay, now, if I now put my other forces in, I can start adjusting magnitudes correctly. Should N1 apply in the X and Y direction? Is there any acceleration in the X direction?
No.
Is there any acceleration in the Y direction?
No.
So N1 should apply. That's telling me that my friction needs to be the same length as my Tx. You guys good? And Ty and normal both go up, so now I'm going to add normal there too. Color helps here. And then down, I'm going to make weight extra long, so that when I add the magnitudes of Ty and N, I should get my weight. Are you guys happy? And now the solution consists of some beautiful logic applied to both the X and Y axis. So you say, okay, the force vectors in the X axis have to add to 0 since acceleration in the X axis is equal to 0. Make sense? So you need to have that N1 statement. That's super important to me. It's beautiful logic. Okay? And then you're like, okay, let's add all the vectors. So in the X direction, what do I have? Okay, so Tx, is that positive or negative? And notice I'm adding to that. What do I add to it? What's the other? Right? And this is going to tell me Tx equals friction equals, well, if I go over here and play the game with the angle, I get the same thing here. You guys good? You guys cool? So Ty, that's the one I try to do first. When I look at a triangle, I'm like, okay, this is the right triangle. Ty's opposite side, so I know it's sine. So Ty is the hypotenuse times sine. So that's my shortcut. So Ty is going to be T sine theta. Again, we already did that. And Tx is going to have a magnitude of T cosine theta. You guys good?
Yes.
So this is going to be equal to T cosine theta. You guys happy? All right. Then I'm going to use N1 in the not X, but and the force in the Y direction I have to add to since help AY. Okay, please don't make any noise for a little bit, if you don't mind. So now I'm going to add all the vectors same as before. Positive normal plus positive Ty. Just give me a minute, I'm almost done here. Plus negative weight equals 0. So typically you might solve for normal. It's going to be weight minus Ty. You guys good? Normal equals mg minus Ty. And you can substitute for Ty. And that's typical problem. Alright?
Okay.
I'm going to put up a worksheet to help you out. Make sure you do it for homework. Have a good weekend. Let's do that. Give me a sec. I want to.